In this part of our class today, we're going to see an example that is going to demonstrate how taking vectors and breaking them apart into their component pieces, the x component and the y component, and working with those smaller pieces is going to allow us to answer questions that at first could seem pretty complicated. But if we can break those down, those more complicated questions down, into component pieces, work with those pieces, and then build back up our answer, we can answer some pretty interesting stuff. Okay, so in this example, we are going to be talking about golfing and a putting green. And here we have a novice golfer who takes 3 strokes to sink the ball on the putting green. The displacements of the strokes are 4 meters to the north, then 2 meters, 40 degrees north of east, and 1 meter, 25 degrees west of south. Alright, so we had that novice golfer, took that golfer 3 strokes or 3 hits to get the ball into the hole. Now, starting at the same initial point, an expert golfer could make the same hole-in-one in what single displacement? Give your answer as a length and angle. Okay, so let's start by analyzing this novice golfer. Okay. So what we're going to do is we are going to look at these putts that this golfer has attempted, and we're going to consider the initial or the starting point as the middle of our XY plane. In our XY plane, up will be north, down will be south. We can label those things if we want to: north, south, east, and west, and we'll think of those as our XY axes or our cardinal directions. Okay, so the first stroke by the novice golfer is 4 meters to the north. So we can draw that vector with its tail at the initial or starting point, draw that vector to a length of 4 units, and directly north. We're going to call that vector vector A. Okay, our next vector, or the next stroke for the golfer, is this golfer putts the ball 2 meters at 40 degrees north of east. So when I think about the direction of north of east, I want to start by focusing on the east part. And then I look at angling north from that easterly direction by 40 degrees. Okay, so we've drawn our vector B, and this is all, I'm not drawing this to scale, but the length of that vector B should be about half the length of the vector A, since B should be 2 meters long and A should be 4 meters long. Okay, so now the ball is sort of a little bit to the right of where it was before and a little farther away than where it should be. And the final putt by this novice golfer is 1 meter in length, 25 degrees west of south. So when I draw this, I want to draw south first and then swing an angle of 25 degrees toward the west side. So this vector I'll call vector C, and that vector should have a length of 1. So that vector, I didn't do a really good job of drawing this on the whiteboard, but it should be half the length of the vector B, because it should have a length of 1, the vector B should have a length of 2. But that's okay. We're just drawing a sketch here. Okay, so what this now tells us is that after those 3 putts, the novice golfer has gotten the ball in the hole. And the question is, starting at the same initial point, an expert golfer would make the hole-in-one in what single displacement? So clearly this novice golfer did not do a very good job of aiming towards the hole, especially on that second putt, since he probably should have maybe aimed a little farther south and a little farther east, but that's okay. So our expert golfer is going to create a hole-in-one, so he's going to start at the initial or the starting point and hit directly to the hole. So his vector, we're going to call this vector R, because this will be our resultant vector. The vector R is the sum of the other 3 vectors. So our goal is going to be to come up with the components for this R vector, and if we can do that, then we can answer questions about the length and the angle of that vector R. Okay, So to determine our vector r, we need both components rx and ry. And in order to find those, what we'll want to do, and this is sort of the crux of the problem, what we're going to want to do is we are going to want to take our vector A and our vector B and our vector C and add them together. And you might recall from last class that when we add vectors algebraically, what we're doing is adding them component-wise. So we are going to figure out the x and y components for vector A, the x and y components for vector B, and the x and y components for vector C. Then we'll add the x components of all three. That'll be Rx. We'll add the y components of all three. That will be Ry. Okay, so we have our work cut out for us. For each of the vectors of the novice golfer, vectors A, B, and C, we're going to break those vectors down into an x and y component. Okay, so we're going to find the components of each of these vectors, A, B, and C. And so we'll start with our vector A, and you might remember that vector A was a vector that was 4 meters north, and this one's actually a little more straightforward because our vector is pointing vertically north, so there is no x change for this vector, so the x component is 0, and the length of our vector is 4, so all of that length is in the y direction. So our components for the vector A are 0 and 4. Okay, so now we go on to our vector B, and vector B was a vector who was 2 meters, 40 degrees north of east. Okay, so we have our vector, and I've labeled on there the x component, which is our horizontal part, and the y component, which is our vertical part. And the length of our vector is 2. So let's start by calculating the x component, bx. And what I notice is that when I am thinking about the x component, that's the adjacent side as it relates to the angle of 40 degrees. And so when I think about that, and the 2 is our hypotenuse, so we're looking at adjacent over hypotenuse, so that's the cosine function. So we have cosine of 40 degrees is bx over 2. And then I can solve for bx by multiplying both sides by 2, and I get that the x component of our b vector is 1.532. As you are doing these calculations, make sure your calculator is in degree mode, and you should double check that you get 1.532. Okay, so now we want to talk about by. So the y component is the opposite side, and we're looking for the opposite side. We're given the hypotenuse, so opposite over hypotenuse is sine. So for 40 degrees, we have sine of 40 degrees is equal to opposite, which is by, over hypotenuse, which is 2. And once I write down that initial equation, I can multiply both sides by 2 and type 2 sine of 40 degrees into my calculator and get that the y component of my vector is 1.286. Okay, so we've just found the x and y components of our vector b, and so we can write down that vector b with the x and y components inside angle brackets. Okay, so now we are ready to talk about our vector c. And the vector c was a putt, it represented the putt of 1 meter in the direction of 25 degrees west of south. Now, when I draw the vector c, some things that I notice about this is because we're thinking of our cardinal directions, north, south, east, and west, as our xy plane, that vector c is showing up in quadrant 3. And so in quadrant 3, both of my x and my y components are going to be negative. So in the end, I'm going to calculate my components by thinking about positive values, but my actual final answers I need to make sure I have the signs, SIGNs, negative for both the x component and the y component. Okay, so one thing that can help me to sort of ignore the fact that I have negatives is to pull the triangle out of the xy plane and label the sides as opposite and adjacent. And another thing that I might notice is that in this new triangle I have an angle of 65 labeled, and that's because the 25 that we're given is not exactly where we'd like it to be. The reference angle is the other portion of our angle, the complement to 25. So to get that, I would take 90 minus our 25 degree angle is going to give us the 65. Okay, so thinking about the adjacent side is adjacent over hypotenuse is cosine, so we have cosine of 65 degrees is adjacent over 1, and so the adjacent side is 0.423. All right, now that tells me the length of the adjacent side, but our CX in our drawing should be the negative version of 0.423 because we're on the left side of this xy plane. Okay, so now I'm ready to talk about the opposite side of this triangle in relation to the 65 degrees. The opposite side, opposite over hypotenuse, is sine, so we have sine of 65 degrees is opposite over 1. And I can solve for sine of 65 degrees, or type that into my calculator, and I get that the opposite side is 0.906. And again, that is the opposite length, but then when I talk about the y component of my vector, that needs to be a negative value. Okay, so we now have both components of our vector c, and so the vector c we can write using angle brackets with the x component first and then the y component, and both of those are negative values. Now, something to think about on this last one. You might say, well, Diane, why can't I use that 25 degrees? And you can draw a triangle a lot of different ways. And so I would encourage you to think about other ways that you could come up with the x component and y component for this last vector c by using the 25 degrees instead of the 65 degrees. You should come up with the same values in the end, just that the way that you get there might look a little bit different. Okay, so now we have all three components, all three vectors and their components. And our job now is to determine that resultant vector, which is the sum of these three vectors. And so the way that we calculate, or the way that we add vectors, is that we add component-wise. So we're going to add the x components of a, b, and c, and then we're going to add the y components of a, b, and c. Now, the way that we can write this is we write Rx, which is our x component of R, is the x component of A plus the x component of B plus the x component of C. And we can crunch some of those numbers. Notice that the C component is still negative. And so when we add these together, we end up with 1.109 for the x component of our final vector. And we can do the same thing with the y components. So when we add those y components, we end up with 4.38. Okay, so we can now write down our resultant vector. This is the vector that describes the path of the expert golfer's ball. So our resultant vector is, with angle brackets, 1.109, 4.38. And so sometimes we might call this the single displacement vector, or because we're adding up a bunch of vectors together, this is called the resultant vector. Okay, so that was a lot of stuff to think about and a lot of numbers to crunch. And you may want to go back and rewatch that part of the video because we went pretty fast through some of that stuff. Pause it along the way and check those numbers. And as you're checking those things, you might end up going back to the first page And on the first page, the question that was being asked is, okay, find that resultant vector, find that single displacement vector that describes the expert golfer's putt, but give our answer in terms of a length and an angle. So we're not quite done yet. We are asked to report in terms of a length and an angle. So our final step in this problem is to take the vector we have and determine the length and the angle. Okay, so we had our original picture, and this had all the pieces on it, and right now it's all being redrawn for us automatically, which is kind of cool. And we had our three initial vectors, or three primary vectors for our novice golfer, and then we had our expert golfer, which is our resultant vector. And we know what our components are for our resultant vector. And our goal is to figure out the length of this vector and the angle, and describe the angle of this vector. Okay, now the picture that we have drawn is from the first page of our video. So I'm going to go ahead and redraw this picture just of the resultant vector a little bit bigger so I can kind of see what's going on without scribbling on that teeny tiny little picture. We have our x component, we have our y component, and we have an angle of theta. So to figure out the magnitude, I can use that formula that we came up with in class last time, which is that the magnitude is the x component squared plus the y component squared, square rooted. And if I crunch all those numbers, 1.109 squared plus 4.38 squared, take the square root of it, I get 4.52. Okay, so that is the length of our resultant vector, and that is the length of the putt that the expert golfer needs to make to get a hole-in-one. Okay, now the last piece of information is how should he angle himself so that the ball will be aimed directly at the hole. In other words, we want to figure out what theta is equal to. And when I look at our drawing of our vector here, I see on this r vector, I see that I have an opposite side of 4.38 and an adjacent side of 1.109. And so if I think about the trig function that works with opposite and adjacent, I want to think about tangent. And so I know that tangent of theta is opposite, which is 4.38, over 1.109. Now my goal is to solve for theta. So to solve for theta, I want to undo the tangent function. And so the way that I can do that is I can take the inverse tangent of both sides. On the left side, that will cancel the tangent function. And on the right side, what I'll be left with is inverse tangent of that ratio of 4.38 over 1.109. Once I write down theta equals inverse tangent of that ratio, I can use my calculator in degree mode to find out that theta is equal to 75.8 degrees. Okay, so we now have the direction and we have an angle. But in terms of the angle, I want to give that angle measurement in terms of the cardinal directions. So we have north and south and east and west. And so our measurement of theta is a measurement of 75.8 degrees north of east, because we started on the east side and we went towards the northern side. So we would say north of east. So once we have all of that information, we can conclude that the golf hole is located 4.52 meters from the starting point at an angle of 75.8 degrees north of east. And that is our final answer. Okay, So I hope that what you're taking away from this example is that when we want to combine a bunch of vectors where a lot of things are happening, I mean, in this case, the ball is being hit 3 times, and we want to compare that to one single hit, that the way we can handle that complicated part, the part about the 3 hits happening and, hitting the ball all over the place, the way we handle that is to take each vector, break it into its component parts, add those component parts together, and that will give us the pieces that we can use to build our resultant vector. Okay, I also hope that some of these videos are giving you a little bit of a flavor of maybe what some of your future classes are in terms of physics and maybe some calculus, where some of this information will be kind of thrown at you pretty quickly in some of those early days in the class. All right, thanks for listening.